Hi, I'm Giuseppe Garofalo, PhD researcher at Distrinet Research Group, and today I will be talking to you about our work on achieving data minimization in motion data sharing settings. As the availability of wearables technologies grows, so do the applications that improve our living standards in both health and fitness domain. In this context, motion data or sensory data capturing human gait is a key asset that can be used as a disease predictors and fall detection system for the elderly. In recent times, there have been proposals to use wearables and data they collect to curb the spread of COVID-19 too. This led to several privacy concerns about the sensitivity of the shared data. In particular, cloud-based service providers like the Google Fit API are making it easier to extract sensor data and process it online. The only protection given by responsible use guidelines and no real technical guarantees against possible misuse of the platform. Additionally, user studies document how people tend to be confused on how fitness trackers handle their data, ending up being less careful when accepting their privacy policies. This is leading to a world where mass-scale data collection is not only real but also acceptable. Law enforcement is our way of defending against these threats. However, the richness in sensory data makes it really hard to understand what is needed for our task and how to exclude what we deem as sensitive and not strictly necessary. We can infer sensitive attributes in structured and unstructured datasets, even though we cannot actually see them. So we need privacy-enhancing technologies that translate principles like data minimization and purpose limitation into objective measures for regulators and tools for the end users. In this talk, I will be discussing our approach to private feature extraction. But first, let's dive into the goal of our work. We want to design a mechanism that fits into existing machine learning pipelines. As usual, in machine learning pipelines, the raw data undergoes a feature extraction process before being fed to a classifier that predicts a target variable. We imagine the situation where the extraction process happens at the user side and the features are sent to the cloud for further processing. There is where the violation of users' privacy happens. The feature extracted for a specific task are used for unintended scopes by the cloud-enabled service provider itself or external companies that gain access to users' data in a way that can be more or less legitimate. Our main goal is to minimize the leakage of the private variable while preserving the target variable accuracy. As a use case, we explore the classification of age and gender as our primary utility goal. These can become, for example, the classification of diseases when enough data will be available, while the identity of the user is the private variable we want to hide. Therefore, we minimize the leakage of private information by hindering the matching capabilities of the service. So when user A shares two separate motion traces, the cloud service will be able to assess his gender, but incapable of linking them back to the same user. The feature extraction process happens locally on the user's device. We derive our threat model from existing work that deal with an honest but curious cloud service provider. They follow the protocol honestly by providing a service to the users, but try to infer as much information as possible about them. That's why no trust can be put on them upon sharing sensitive data, and only what is strictly necessary for our primary goal has to leave the user's device. Our approach can be divided in 4 steps. The first one being the selection of the model to be privatized. In our case, we select a recent state-of-the-art model in age and gender recognition. It takes as input sensors data measured by accelerometer and gyroscopes and extract a set of features to be used for the prediction of age and gender. In particular, temporal convolutional networks, a kind of neural networks that copes with temporal data, is used as a feature extractor. The features are then classified by a second network that outputs an estimate of either the gender or the age of the input user. In order to minimize the leakage of identity, we define a pluggable component. Intuitively, it tries to minimize the distance between samples belonging to the same user and maximizes the distance of samples belonging to different users. Since we are interested in minimizing the information about the identity and preserving the information about the gender or the age, the three components are joined in an adversarial framework. Here they compete with each other, each with its own optimization goal. For how exactly our optimization works and other details, please check out our paper. After the optimization, the feature extractor is retained and shared with the users. This way, they can perform local data processing and send the features to the service provider. This is just a minimal representation with respect to the main task, such that it is not possible for the service provider or other third parties to link the traces to the same user. In line with related work, our privacy and utility are estimated by performing supervised learning on top of the derived features. We freeze the feature extractor after training and retrain a model that aims at extracting the identity and the age or the gender of the users. Two sets of disjoint users are used for this task, a training set and a test set. In order to compare our approach with existing ones, we consider other pluggable solutions or solutions that do not require the model to be re-engineered. The baseline is represented by a model optimized for the primary task, the estimation of age and gender, with no further optimization. Then we test two approaches proposed in the literature that are noise addition at the sensor level and the training of our model in a non-adversarial environment, meaning that no competition between the different components and the joint optimization strategy for all of them is devised. By training the original selected model, we inspect the retainment of identifiable information in the feature space. The utility is given by the F1 score for the gender, meaning a higher value is associated to a greater utility, and the mean absolute error in terms of years for the age, meaning greater values are associated to a decreased utility. We found that utility to be in line with the state of the art and aim at keeping these values as close as possible to the baseline when performing privatization. On the other end, the identity verification is measured as the percentage of pairs that are correctly recognized as belonging or not to the same user. This is the value we want to decrease up to the point where it's not possible to tell if two samples belong to the same user or not, or a random guess of 50%. The first privacy enhancing strategy we test is the addition of uniform noise at the sensor level. On the right, you can appreciate how adding noise is effective in reducing the identifiability of the user, the red line, but at the same time penalizes the primary utility at the point where it becomes useless for the main task. In the table, the results for a given privacy level of 60% of identification accuracy. In brackets, you can see the difference between the actual technique and the baseline. We lose 10 points in the gender accuracy and 2.5 years in the age estimation task. Thus, we wonder if optimizing our network as a whole without making use of the adversarial framework would help in achieving a better trade-off. We found out that despite keeping a high utility for both gender and age, the identity verification accuracy is not affected by the addition of the pluggable component. This is due to a lack of generalizability in the approach that is only able to trick a very specialized adversary instead of a more powerful one that can adapt to the changes in the feature extracted by the user. This is what our approach achieves by performing continuous adaptation via adversarial optimization. In the end, the best trade-off between privacy and utility is found, with an identification accuracy around 65% for the age and a more successful 57% for the gender. This comes at no cost in terms of accuracy compared to context-free noise addition. In case of the gender, we even witnessed an increase in test accuracy of 1 point. To conclude, in this work we verified the possibility to use data-driven strategies to achieve privacy by design without having to rethink existing models or just by adding an unpluggable component. We should consider building tools that can help regulators to assess the privacy guarantees advertised by companies and at the same time allow the users to handle their data in a more aware and conscious way. Limitations to our work include the absence of formal privacy guarantees and the possibility of re-identifying a person over multiple rounds of sharing across different services. We can overcome these limitations by bringing together data-driven strategies and crypto-oriented techniques, or formally proven techniques, like differential privacy. Hybrid techniques might allow to improve existing privacy trade-off. Lastly, we only evaluated a very specific use case. Further experiments are needed to verify the applicability of the same techniques across different domains by using several attributes as our target objective and providing tools for fine-grained tuning of privacy at the user side. I thank you for joining this talk.